All right, cool. So we kind of got to jump on this chapter last week, so we just got two quick reactions to cover here to close out our discussion of aldehydes and ketones. All right. They're both named after scientists here. The first one is what's called a Wolff-Kishner reaction. All right, and what we're going to do is we're going to take an aldehyde or ketone and we're going to react it with what's called hydrazine. Hydrazine is an amine, but those two nitrogen, I guess it's actually not an amine because there's no carbons in it, but those two nitrogens are attached to one another, all right? But what I want you to do is see if you can't predict the products of this reaction, just treating this hydrazine as if it were a primary amine, all right? Last class we discussed how nitrogen nucleophiles react with our aldehydes and ketones. So see if you can't predict the product if we just pretend like this hydrogen is just a regular old primary amine. All right, so remember these nitrogen nucleophiles were weird. These produce what were called imines, where our oxygen-carbon double bond gets replaced with a nitrogen-carbon double bond. So if we're using hydrazine as our primary amine here, we get this carbon-nitrogen double bond, and then it's still got that other nitrogen attached to it as well. Cool, so that's all well and good and what we, consistent with what we learned last time. Really what makes a Wolff-Kishner reaction is first doing this hydrazine step, but then treating this with KOH. All right, and we're not going to look at any mechanism, but what happens is you will lose a nitrogen gas molecule. Those nitrogens will come off of that molecule, and you'll be replaced with just hydrogens. So we talked about how we can reduce aldehydes or ketones to alcohols, but this is now how we would fully reduce that carbonyl carbon, right? We replace all carbon-oxygen bonds with carbon-hydrogen bonds, right? In effect, this Wolff-Kishner reaction is a way to chop off that carbonyl group. All right. So let's just say Wolff-Kishner, this is how we fully reduce a carbonyl carbon. All right, and so again, this is not one that we're going to have a mechanism for or anything like that. So to be clear, what we need to be able to do is to site recognize these reactants here, or rather these reagents. Again, this reaction would first treat with hydrazine, and then follow up with potassium hydroxide in order to fully reduce that carbonyl carbon. And of course, you don't have to draw in those implied hydrogens. I'm just trying to make a point here. Cool. All right. Our other random reaction here is what's called a Wittig reaction. This is when we take our aldehyde or ketone and we treat it with what's called an Aldehyde, or at least that's how I pronounce it because I've never heard anybody else say it. I just read it in the book, so you pick one way and you roll with it, all right? But yes, this thing here is a little weird. We got this PPH3 where that phosphorus is double bonded to another carbon. Okay, so first of all, PPH3, triphenyl phosphorus. All right, this isn't really all that big of a deal, but let's just point it out here. That means that we have this phosphorus atom bound to 3 benzene rings. Weird paddle-shaped molecule here. These are terribly ugly, but we're gonna go quick. And then double bonded to a carbon. All right, so this is my Aldehyde. All right, so kind of weird. I'm going to be honest, there's not much that's like just intuitive about this reaction. You don't look at this molecule and be like, yes, I know exactly what's going to happen here. No, all right? But it does have one incredibly cool purpose here. These reactions, what will happen is we're going to replace that carbon-oxygen double bond, replace that oxygen with whatever is on the other side of that Aldehyde. So we form a new carbon-carbon double bond here in the place of our carbonyl oxygen. All right, there is one important restriction on what your Aldehyde can be. All right, this can be at most a mono-substituted carbon. All right, there's that H and that R group. I don't care what that R group is, but there has to be a hydrogen on that carbon as well. All right, so then let's just do a specific example here. We're going to take 3-pentanone. All right, we're going to react it with this thing here. Okay, everybody take a second and see if you can't give me the products of this reaction, the organic product of this reaction. right? So again, not something that I would just be like, oh yes, I can totally see this, right? But we're going to pick this thing up and we're going to attach it to where that carbonyl bond used to be, all right? So I'm going to still have my ketone, I'm going to still have a double bond in that exact same place. It's just no longer a carbon-oxygen double bond, it's a carbon-carbon double bond, all right? So we managed to turn our ketone or aldehyde into an alkene. You may or may not do this in the lab. They work pretty well, not great, but yeah. Nonetheless, this would be a way that we can convert our ketone or aldehyde into an alkene using, again, this weird Aldehyde reagent here. Cool. All right. We talked a lot about a lot of different reactions. So let's just try to summarize some, making one of those little reaction wheels here. All right. We're going to put a simple ketone in the middle. We'll use acetone just because it's nice and small. All right. And we want to try to fill this in here with a bunch of different reactions that we learned from this chapter. I'm going to give you all a few minutes, see if you can't fill in this reaction wheel here. All right, so let's look here. The Grignard reactions are ones that we would have studied. Actually, both of these were ones we would have studied in the last chapter. All right, both of these will convert your aldehyde or ketone into an alcohol. For our Grignard reaction, we have this new carbon-carbon bond, whereas for our hydrides, we are reducing that carbonyl to an alcohol, and we create a new carbon-hydrogen bond, which I'm going to draw explicitly just to make a point. These mechanisms were incredibly similar here, all right? And importantly, the lithium aluminum hydride and the Grignard, are these acidic or basic nucleophiles? Cool, so I think everybody's gonna look at this set of reagents here and be very tempted to say acidic because of the H3O here. But remember, that is a completely separate step after that nucleophilic addition. Both of these are considered to be basic nucleophiles. You will only see negative charges in your mechanism, okay? So don't let that H3O fool you. That is a separate step after that nucleophilic addition step. Cool. All right, so then if we react this aldehyde or ketone with water or an alcohol, would this reaction be under acidic or basic conditions? So they're neutral nucleophiles, right? But we have to be careful. These are way too weak of nucleophiles to react under just normal conditions. You do need to sort of juice things up by having acidic conditions, which will turn your aldehyde or ketone into an even better electrophile so that it can react with these weak nucleophiles. With water, we get that gem diol, where we have those two OH groups. We said that this equilibrium actually favors the ketone or the aldehyde, but importantly, this reaction is always occurring in solution. They're flip-flopping back and forth and back and forth and back and forth. Under acidic conditions with our alcohol, we get something very similar. All right, but we kind of made a point here to note that, yeah, okay, first you'll get what you expect with that single addition of your nucleophile. All right, but then this thing is actually going to keep on reacting until you have an addition of a second alcohol as well. Okay, We called these things acetyls, and we said that they're very important in organic chemistry and actually more important in biochemistry. They kind of play an outsized role in this chapter because of that. This is how sugars get linked together in a cell. So let me see if I can squeeze this all into one line here. All right, if we react our aldehyde or ketone with a primary amine, we're going to get that weird imine, amine to imine, where we see that carbon-nitrogen double bond. If we react it, let's jump to the other side here. If we react it with a secondary amine, it wants to do the same thing. We showed in our mechanism, we get all of the same steps up until that very last step where there's not an extra hydrogen to remove from that nitrogen. So instead, it comes from that neighboring carbon forming these enamines. Okay, and then if we use one of these cyanide nucleophiles, we get our nucleophilic addition. All right, but importantly, there were two follow-up reactions that we learned here as well, using either acid and heat or our reducing agent, lithium aluminum hydride. See if you can't remember what these follow-up reactions did to those nitriles. Right, so these were oxidation or reduction reactions if we use the acid and heat. So importantly, we always keep that same hydroxyl group that we started out with. What's going to happen is we're going to modify that nitrile carbon. So acid and heat will produce a carboxylic acid. All right, and remember, I've added this additional carbon when I put that nitrile on there. That's why I have an extra carbon in my product here. I start out with a 3-carbon aldehyde, but as soon as I add that nitrile in there, now I got 4 carbons. Everybody always loves to forget the carbon at the base of the triple bond, all right? Don't forget. And then instead, if I did lithium aluminum hydride, I would reduce that group. All right, and since it's a nitrogen, it doesn't reduce to an alcohol, but rather to an amine. Cool. All right. These little reaction wheels are great study tools, right? Of course, at first you're going to have to cheat and look in your notes. Ideally, by the end of the exam, you're going to start with a blank reaction. By the end of the exam, before the exam, you're going to start with a blank reaction wheel and be able to fill these in on your own, right? Great little practice tool. If we're being really good and you can just put it in your notes here, we should also include, to just summarize everything, what we learned today, those Wolff-Kishner, as well as that Wittig. We're running out of room here. All right, but that would be our full reaction wheel for this chapter. Cool. All right, I'm going to take these last few minutes here to sort of just introduce our next chapter, which is again going to focus on aldehydes and ketones, but in a completely different light. All right, this is what's called alpha carbon chemistry. Okay, if we take an aldehyde or ketone, let's just look at an aldehyde real quick. All right, there's something about this aldehyde that we've discussed over and over again, which is that it has a good electrophilic site. Where is that electrophilic site on our aldehyde or ketone? Carbonyl carbon. All right, so when we look at this thing here, we see that this is glowing bright blue because it's a good electrophile here. All right, cool, and that is what has governed our sort of understanding of aldehyde and ketone chemistry up until this point. All right, the fact that that carbonyl carbon is an electrophile. Electrophilic carbonyl carbon. Cool? Now we're going to sort of pivot here. There's another aspect of aldehydes or ketones that is going to lead to another branch of reactions. And that has everything to do with this carbon right here, which we call the alpha carbon, the one that is right next door to our carbonyl carbon. All right, and this is pretty typical for functional groups. They start using Greek letters to talk about the carbons that are farther away. So this would be the alpha carbon. The next one would be the beta carbon. The next one, the gamma carbon. I don't really know how the Greek alphabet goes after that. Delta, epsilon, I don't know, doesn't matter. We're focused on the alpha, okay? That one right next door to our carbonyl carbon. All right, and what we're going to see, the reason why we're going to focus on this alpha carbon is not actually the carbon itself, but the hydrogen that's on that alpha carbon. All right, there's something special about this hydrogen that is very, very rare for hydrogens that are attached to carbon atoms, and that is that this hydrogen is relatively acidic. All right. And what do I mean by acidic, right? Remember, acids are proton donors, and that sounds all nice and neat, like, oh, you're giving it away. Some acids are a little bit more stubborn. You got to pull those hydrogens off, but the bottom line is that hydrogen can be removed. All right, and in contrast, why is that such a big deal? Well, if we just take a regular alkane, right? Those protons are quite literally the least acidic protons you could ever have in your entire life, right? A hydrogen, like a carbon atom, is going to be the least likely atom to give up a hydrogen. Out of all the elements on our periodic table, carbon's the one that's the hardest to wrestle hydrogen atoms away from, right? So we're going to make a big deal about how for aldehydes and ketones, on that one particular site, on that alpha carbon, those hydrogens are actually relatively acidic. And this is going to be important, open up a whole new branch of reactions for these compounds here. Okay, what we're going to sort of talk about and end with today is what's called the keto-enol tautomerization. And a tautomerization is an internal rearrangement of atoms. So it turns out that any ketone or aldehyde, but let's look at our simple acetone here. Is always in equilibrium with an enol, where you have a carbon-carbon double bond located directly next to an alcohol group. And I know everybody's like, oh man, I remember this from when we were talking about alkynes. It was important for the hydration of alkynes and why you got aldehydes and ketones as your products, all right? Importantly, this equilibrium here very much so favors the aldehyde or ketone. All right, but again, just because you have a little teeny tiny amount of it in solution doesn't mean it's not super important for the chemistry of that molecule. Right? If only 0.01% of the population is going to form an enol, it's still going to be important if that enol then goes on and reacts and does other stuff. Right? So, again, we have our ketone in equilibrium with this enol here. And again, we're going to see that's super important for the chemistry of that molecule. Now we call this an internal rearrangement, meaning if I counted the number of carbons, atoms, and hydrogens on one side, I have the same carbons, atoms, hydrogens on the other side, all right? So importantly, what happens is I start out with this hydrogen over here on my alpha carbon, but again, that hydrogen's relatively easy to remove, so that ends up swapping places and coming up here onto that oxygen atom. Right? So that's my internal rearrangement here. Now, in truth, it's not the same hydrogen. It doesn't just jump from one atom to the other. This reaction can be catalyzed by either acidic or basic conditions. So let's look at our acidic conditions mechanism. So if we play the spot the difference game here, we need to break this bond between carbon and oxygen, or carbon and hydrogen. We need to break this bond between carbon and oxygen. And we need to reform a new bond between carbon and hydrogen, oxygen and hydrogen. as well as our new carbon-carbon double bond. All right, so under acidic conditions, we can't just break this pi bond and give that pair of electrons to that oxygen because that would give it a negative charge. So we're going to do the same strategy that we've seen quite a bit, where we manage our charges by protonating that oxygen. If we're under acidic conditions, what's our base that we're going to use? Just water. All right. And I'm going to tell you, we just got one more step to get to our enol product. I want y'all to see if you can't figure this out, how we get from A to B here. I want you to think elimination type mechanism here. All right, but let's draw where we're going. That's always super helpful. All right, how are we going to get from A to B on this one? We're going to have to do quite a few jumps all in one step. All right, quite a few electron pushing arrows all in one step here. Let's see if you can't close the gap to get from A to B on this one. Cool. All right, so we got to remove that hydrogen, so that's what our base is for. All right, and importantly, we see this a lot with our elimination mechanisms. Where does this pi bond pair of electrons come from? Well, that's that pair of electrons that was in that carbon-hydrogen bond. All right, so that's going to come down and form my pi bond, but I can't be breaking that carbon atom's octet, so that pair of electrons jumps up onto my oxygen atom here. All right, cool. We can do the same thing under basic conditions. All right, we got the same reactant and product under basic conditions. We just got different rules for what's allowed when, what charges are allowed, all right? And so we're going to see that the order in which we have these events is going to switch here. All right, but see if you can't take a second and work through what it would be in basic condition. I'm going to give you all a little bit of head start, and then I'll put it up here for you to check out when you're done, or if you're stuck. All right, so now we're actually going to have that alpha hydrogen removed first because we have that strong base in there. This produces that alkoxide intermediate, but that's allowed because we're under basic conditions. We're allowed to have negatively charged intermediates. So then my last step in the mechanism is that protonation of what is now my alcohol oxygen. Right, so kind of the reverse order of what we did last time. And again, you can see that we used those proton transfer steps to manage our charges, so we didn't have any illegally charged intermediates. Cool. All right, and we'll pick up with this alpha carbon chemistry business next time. Enjoy y'all's weekend.